The time needed to utilize JWST's state-of-the-art technology is substantial. Once the telescope is in space, it will be exceptionally difficult to ensure that the mirrors are impeccably arranged so it can focus on distant universes. Small engines, called actuators, hold the key to this issue. It has 6 actuators on the back of each mirror segment, which includes the primary and secondary mirrors. These make it easier to make the small adjustments needed to achieve the best focus. Additionally, there is an extra actuator in each primary mirror segment that allows you to change its shape, ensuring that the arrangement is optimal. The third mirror, on the other hand, remains static, polishing off the complicated system for moving mirrors. However, keeping Webb's mirrors at the right temperature is another challenge. Webb needs to operate in the infrared range to observe the faint infrared light that the earliest stars and galaxies emit. To prevent interference, the telescope's mirrors must be much cooler than those on the Hubble Space Telescope. This is because warm objects emit infrared radiation. Therefore, Webb's mirrors are cooled by cryogens to about -220 degrees Celsius. While it's freezing outside, the telescope must remain sensitive to infrared signals from far-off celestial bodies. Webb was deployed into deep space, far from Earth's heat, to create and maintain this freezing environment. Sun shields are essential because they protect the mirrors and sensors from the sun's rays, while also keeping them away from the spacecraft, which is already quite warm. This smart thermal management system keeps Webb's mirrors at the right temperature, enabling groundbreaking studies of the universe's oldest and strangest events. However, its valuable data doesn't just travel through space on its own. It relies on a complex network of communication. The telescope sends its data to a tracking and data relay satellite system, which begins this cosmic transmission. From there, the signal travels back to Earth and lands on it. The remarkable spirit of global collaboration behind JWST's mission makes it even more exciting. This isn't just a NASA project, it's a joint effort with the European Space Agency. The James Webb Telescope demonstrates how innovative and cooperative people can be when they work together to explore space. With cutting-edge technology and a willingness to collaborate, Webb helps us learn more about the universe as we continue our journey through space. It stands as a symbol of our boundless curiosity and desire to solve the mysteries of the cosmos. Each groundbreaking observation sheds light on the vast unknown, studying the mysteries of the universe as a significant step forward in our search for answers about the cosmos and our origins. Webb explores the universe's past from just after the Big Bang to the complex processes that shape galaxies, stars, planets, and even our own solar system. Webb's infrared vision allows us to look back over 13.5 billion years, making it a cosmic time machine. Because it is so sensitive to infrared radiation, scientists can study faint ancient galaxies and compare them to current structures in the sky, like spirals and ellipticals. By examining these, Webb shows how galaxies have changed over billions of years. The Webb Space Telescope can also see through thick dust storms, which make it difficult for visible light telescopes like the Hubble Space Telescope to observe. By looking through these dust clouds, Webb reveals the complex processes that lead to the birth of stars and planetary systems. This helps us understand how the universe has evolved over time. Webb's infrared capabilities allow it to study planets beyond our solar system, giving us clues about their atmospheres and perhaps even the building blocks of life elsewhere in the universe. In our search for alien life, we are examining both distant planetary systems and objects in our own solar system. Webb is an excellent telescope for studying exoplanets because it can detect slight changes in the infrared signals of these distant worlds. Although it primarily uses an infrared camera, by observing these atmospheric compositions and characteristics, the telescope may be able to determine where exoplanets came from and whether they could support life. One way the James Webb Space Telescope searches for exoplanets is by using the transit method, observing how the starlight dims when a planet moves in front of its host star. Astronomers call this a transit. Collaborating with telescopes on the ground enhances this project since they can measure the planet's masses using the radial velocity method. Webb then uses spectroscopy to examine the exoplanet's atmosphere. The telescope has coronagraphs that make it easier to take direct images of exoplanets near bright stars. The final image may show a spot instead of a full scene, but analyzing this spot can reveal much information. Webb uses spectroscopy to examine the exoplanet's color, how it changes with the seasons, its vegetation, rotation, and weather patterns. Webb will play a major role in planetary science after its mission, especially as there won't be any dedicated expeditions to the outer solar system for some time. Observing new celestial bodies and satellites and studying how large planets change with the seasons will be highly beneficial for future planetary missions. Do you think we'll ever get a good look at what the mystical city of God truly looks like? Post your reply below, and click like if you want to see more. On October 9th, NASA observed an exceptionally bright explosion of light from a cosmic event called GRB 221009A, which made its way all the way to Earth. This light show came from a star that exploded far away in space, marking it as the brightest one we've ever seen. Astronomers around the world are incredibly excited about this discovery. What might this cosmic explosion reveal about the mysteries of the universe? Let's dive into what happened with GRB 221009A. Gamma rays are the most extreme type of light energy we know, formed from the most violent astronomical events like star explosions, black holes, or even atomic impacts. These rays are so powerful that they can seemingly tear through the very fabric of the universe. When GRB 221009A arrived, it kicked off a wave of urgent scientific examination. Researchers are now racing to determine where it came from and what it means, pulling in data from telescopes and space missions every minute. But what are gamma ray bursts? They're explosions in space that happen in mere seconds yet release more energy than the sun will emit in its entire lifetime. Scientists think they occur when massive stars collapse or when neutron stars collide, forming black holes or very fast-spinning stars called pulsars. Though the details are still somewhat fuzzy, it seems that when these massive stars collapse, they spin rapidly, create intense magnetic fields, and shoot out jets of particles at nearly the speed of light. These jets emit gamma rays, which we can detect with satellites and telescopes. Even though they're extremely powerful, these gamma ray bursts are usually too far away to harm us on Earth. However, they're fantastic tools for learning more about how stars are born, how they die, and other big questions about the universe. So, what makes GRB 221009A so extraordinary? Researchers are scratching their heads trying to pin down what caused such a massive burst. Perhaps a giant star met a violent end, or maybe two massive stars collided. This event has sent astronomers on a quest through space, gathering clues and understanding this mysterious burst. Each new piece of data from space is like a treasure, possibly holding answers to these big cosmic mysteries. There's a lot of talk about what GRB 221009A might mean for Earth. Could it be a sign of impending disasters? Could it affect our planet in ways we haven't even thought about? These are the kinds of questions that keep scientists up at night. Though the burst itself isn't a direct threat, it's far too distant. It might still have indirect effects that we need to understand. GRBs like this one are incredibly intriguing. Their sheer power and potential for discovery make them extraordinarily important to study. As scientists dig deeper, using every tool and telescope available, they're learning more not only about GRBs but also about space itself. Observatories all over the world, from Antarctica to the mountains in Chile, are working on this puzzle. Space probes are also essential, traveling far beyond our planet and sending back data that gives us a peek into the farthest corners of space. These missions are fundamental to piecing together the bigger picture of how the universe works. Space is vast and mysterious, and not everything makes sense yet. Dark matter, black holes, and the very nature of space-time are all enormous puzzles that scientists are eagerly trying to solve. Understanding more about space helps us appreciate just how incredible it is. The universe is a masterpiece of natural wonders, from the beautiful spirals of galaxies to the explosive deaths of stars. But it's not all beautiful and fascinating. Space can be dangerous too. Gamma ray bursts and asteroids remind us that the universe is also a place of chaos and destruction. Looking at the stars can make us feel small and insignificant, yet it also inspires us with wonder and curiosity. It drives us to keep exploring and learning, no matter how dark or mysterious things may seem. The star that died to create this burst was a true giant, over 30 times the size of our Sun. When it died, it went out with a bang, creating a black hole and sending a beam of gamma rays across the universe. Scientists observed this light show using telescopes on Earth and in space, following the afterglow, which is like the echo of the burst. This glow was so bright in both optical and infrared light that it gave researchers a unique opportunity to study it in detail. This is significant because gamma-ray bursts can tell us a lot about how the universe works, from how fast it's expanding to where galaxies are located. They're like markers in space that help us draw a more accurate map of the universe. The extreme brightness of GRB 221009A means it could even help us measure the universe's expansion more precisely. It also raises some intriguing questions as it was brighter and lasted longer than what our current theories predict. This has led some scientists to think there may be new rules of physics at play. Brendan O'Connor from George Washington University noted that this burst was 10 to 100 times brighter than a typical burst, a rare phenomenon that has experts rethinking some of their old ideas about star deaths and black holes. Usually, bursts like these fade quickly, but not GRB 221009A. Its afterglow lingered, allowing astronomers to get a good look at the details of what happened. They're hoping to study the star itself and the black hole it became. It's truly fascinating that this burst could help scientists learn about dark matter, the mysterious substance that makes up most of the universe's mass yet doesn't emit light or energy. Because gamma-ray bursts are so energetic, they might reveal how dark matter behaves, which would be a major breakthrough. Raffaella Margutti of Northwestern University also commented on the event, noting that the burst was many times more energetic than typical explosions. She described it as the universe showing its dynamic nature, quietly expanding and occasionally erupting with these violent explosions. These bursts, including GRB 221009A, are rare but incredibly informative. They give us glimpses into the most extreme conditions in the universe, conditions that we can't reproduce here on Earth. Each new burst brings a flood of data that can confirm or challenge our theories, pushing the limits of what we understand about space. Beyond the pure science, understanding gamma-ray bursts has practical benefits too. For instance, they represent a radiation risk to astronauts and satellites. By studying these bursts, we can better prepare for those risks, which is crucial as we send more missions into space. GRB 221009A also highlights the importance of international collaboration in astronomy. Observatories around the world, including space telescopes, work together to track this burst and break down the data. This type of collaboration is essential for piecing together the big picture of the universe. In summary, this burst wasn't just a massive display of light, it was a reminder of how much there is still to learn about the universe. It challenges us to keep questioning and exploring, to re-evaluate our theories, and to expand our understanding. Perhaps it's a step toward solving some of the biggest mysteries in cosmology, like dark matter and the fate of the universe itself. GRB 221009A shows us exactly how dynamic and alive the universe is. When Andrew Kosick of the Antarctic Environment Program identified the gamma-ray burst through satellites, he immediately utilized an Earth-based radio antenna to quantify its impact. Considering the blast's outrageous strength and the limited data we typically have on such massive astronomical events, his quick response was key. It demonstrated the passion, and sometimes competitive nature, within the academic community to analyze and publish findings on these intriguing events. Kosick's study showed a clear connection between the burst's waveforms and a spike in Earth's surface electrical activity. This relationship illustrates the complex interactions that high-energy events have with our planet. Although gamma-ray bursts are generally too far away to affect Earth directly, they provide significant insights into the most intense cosmic phenomena. This direct association might seem exaggerated to the public, as it's intended more to reassure than to alarm. However, among scientists, such findings spark debates about the potential impacts of these bursts. The fact that the burst's energy reflects changes in Earth's electrical currents suggests these massive events could have more direct influences on our planet than previously thought, perhaps even temporarily affecting our electromagnetic environment. Moreover, the possibility that a gamma-ray burst could impact geological phenomena challenges conventional models of cosmic interactions that don't typically account for interconnected elements between celestial events and terrestrial outcomes. Critics, however, caution against drawing immediate conclusions from these complex connections. They argue that the precise correlation found by Kosuk could be due to limited data rather than a definitive cause-and-effect relationship. These skeptics believe that simplified models might not capture the full complexity of how cosmic rays interact with Earth's environment and magnetic fields. Despite these concerns, Kosuk's findings are viewed as a significant, though preliminary, validation of existing models. They showcase the scientific benefit of seizing the opportunity to link a cosmic phenomenon with measurable changes on Earth, potentially exaggerating the connection due to the novelty and excitement of the observation. This race to publish findings reflects a broader issue in the academic community: the tension between the rapid release of study results and the slower, more rigorous processes needed to ensure their accuracy and reliability. The strong desire to connect a spectacular gamma-ray burst directly with changes in Earth's electrical currents highlights this dilemma but also emphasizes the need for well-supported scientific conclusions. Kosuk's work raises questions about the long-term effects of such cosmic events on Earth's systems. Could repeated bursts permanently impact Earth's electromagnetic properties? What are the broader implications for our environment if such events were to become more common? These considerations underscore the need for detailed, long-term studies on the interactions between gamma-ray bursts and Earth systems. Researchers continue to explore these phenomena, aiming to deepen our understanding of the universe's impact on our planet. The investigation into the gamma-ray burst GRB221009A and its effects provides significant insights into the intricate interplay between cosmic and terrestrial phenomena. While the initial findings are compelling, they also open up new questions and challenges, suggesting that the scientific narrative surrounding such events is often more complex than it initially appears. Andrew Levon, an astronomy professor, facilitated this investigation by discussing the burst's effects on the ionosphere, Earth's upper atmosphere. He noted that gamma-ray photons having no charge do not interact with magnetic fields. However, their high energy levels can ionize atoms and particles, creating charged particles in the ionosphere. These particles briefly alter the ionosphere's electrical properties, causing disturbances similar to those from solar flares. Though the mechanisms are similar, the effects from this burst were brief and localized, showing the burst's energy was insufficient to disrupt electrical systems globally. Levon's comparison to solar flares helps the public understand these interactions, but it may also oversimplify the burst's complex effects. He reassured the public that the burst did not significantly disrupt technological systems despite its power. However, this reassurance might downplay the potential scientific insights these bursts offer into high-energy astronomy and ionospheric dynamics under extreme conditions. By focusing on the absence of severe impacts, Levon may have unintentionally overlooked deeper investigations into how such bursts could more significantly affect Earth if they were closer or more frequent. His findings, while valuable, represent just a snapshot of the potential interactions between gamma-ray bursts and the ionosphere. These events refine our models of atmospheric and magnetospheric responses to external forces, essential for improving predictions of space weather effects on Earth. This is crucial not only for the safety of astronauts and satellites, but also for understanding the fundamental forces at play in the universe. Studying how gamma rays interact with the ionosphere also helps scientists learn about the origins of these bursts, such as massive star collapses or neutron-star mergers, which typically cause these explosions. These cosmic laboratories provide unique conditions to test theories of particle physics and relativity, potentially leading to new discoveries that could reshape our understanding of the universe. Despite the ionosphere's quick recovery post-burst, the need for precise and rapid data collection during such events is clear. This necessity underscores the importance of continued and enhanced monitoring of cosmic phenomena. Figuring out the ionosphere reactions safeguards present-day innovation and enhances our insight into space sciences. Leon's cautious remarks about the explosion's negligible disturbance underscored the need for continuous caution and improved global collaboration in studying high-energy phenomena. Enhanced technological capabilities and global cooperation could provide more comprehensive information, better preparing us for potential future impact events. Events like gamma-ray bursts consistently test the delicate balance between understanding observable phenomena and theoretical predictions. These bursts challenge our knowledge of Earth's atmospheric shield and stretch the boundaries of our comprehension of high-energy astronomy. Kochik and Lavin's work, while initially reassuring, opens the door to a universe brimming with dynamic and violent interactions that invite us to look deeper and ask more probing questions about our place within the cosmic tapestry. Arati took a deep dive into how the universe's largest stars meet their dramatic ends, collapsing into black holes. This incredible breakdown isn't just the final step of a massive star but also the birth of something equally massive and potentially catastrophic. As these colossal stars collapse under their own gravitational pull, the outer layers rush toward the core, triggering the formation of thin, high-velocity jets that shoot out at nearly the speed of light. These jets are responsible for creating gamma-ray bursts, GRBs, which are intense beams of radiation that travel across the universe. Despite the October 9th gamma-ray burst, known as GRB 221009A, being a spectacular cosmic event and relatively close in astronomical terms, Gödel reassured everyone that it poses no threat to Earth. He explained that a gamma-ray burst would need to occur within our own Milky Way and only a few thousand light-years away to potentially harm our planet, especially affecting the ozone layer. However, he emphasized that such close events are extremely rare. GRB 221009A, at 2.4 billion light-years away, is far too distant to affect us, Gödel clarified, highlighting our safe position from this distant cosmic fireworks display. The distance of GRB 221009A ensures that when its gamma rays reach Earth, their energy is significantly diffused across space, rendering them harmless yet still a magnificent sight for astronomers. This burst serves as a reminder of the universe's dynamic and sometimes violent nature but also underscores the rarity and fascinating science behind potentially dangerous GRBs. Gödel's insights reveal the dual nature of gamma-ray bursts. They're captivating to study and critical for understanding the universe's extreme events, but they also pose a hypothetical, if unlikely, danger under certain conditions. The rarity of GRBs close enough to affect Earth offers some comfort but is a clear reminder of our vulnerability to cosmic phenomena. The life cycle of a massive star is complex and often ends dramatically in its final stages. As the star exhausts the nuclear fuel sustaining it, massive gravitational forces cause the core to collapse, leading to the creation of a black hole or a neutron star. This collapse also triggers the outer layers of the star to fall inward with great force, creating accretion disks around the newly formed black hole. These disks are where conditions are just right to form the jets that produce gamma-ray bursts. When these jets penetrate through the star's outer layers, they emit the gamma rays we observe. A gamma-ray burst can last from a few milliseconds to several minutes, releasing as much energy as the Sun would over its 10 billion-year lifetime. The aftermath of such a burst can also lead to a supernova, further dispersing elements like iron and nickel across the universe, which are essential for forming new stars and planets. Researchers like Gödel study these phenomena not merely out of curiosity but to better understand the processes governing energy and matter in the universe. Each gamma-ray burst provides valuable data that helps refine our models of how stars die and how black holes form, contributing to our broader understanding of the universe. Studying these bursts also has practical implications for protecting Earth. By understanding distant gamma-ray bursts, scientists can better prepare for any potential threats within our galaxy, enhancing our defenses against these and other cosmic threats like asteroids and solar flares. As the glow of GRB 221009A fades, astronomers like Rafaela Margue from the University of California, Berkeley, are closely monitoring the transition from jet light to supernova light. This shift provides crucial insights into the life cycles of stars and the processes leading to their explosive deaths. Margui's team is particularly focused on the spectral features that will confirm the burst's origins and link it to the violent death of a massive star. The current emission is rapidly declining from the jet, while the light from the supernova is becoming more prominent and is expected to peak around 15 days after the burst. Marguerite explains that her team's observations could provide key evidence linking this gamma-ray burst to a supernova, offering a fascinating glimpse into the destructive yet creative power of massive star deaths and black hole births. The detection and analysis of gamma-ray bursts like GRB 221009A are not just academic exercises. They are essential for testing physical theories under conditions that cannot be replicated on Earth, providing a unique laboratory for studying high-energy physics and improving our understanding of fundamental forces and particles. These efforts also underscore the need for global collaboration and advanced technology to monitor and study cosmic events. Understanding how gamma-ray bursts interact with the ionosphere, for example, protects satellites and communication systems essential for both daily technology and national security. The ongoing study of GRB 221009A embodies the dynamic field of astronomy, where each observation can challenge existing theories and push the boundaries of what we know about the universe. The data collected helps scientists piece together the puzzle of cosmic evolution, enhancing our ability to navigate and potentially mitigate the impacts of celestial catastrophes. This pursuit of cosmic knowledge is driven by both the desire to understand the universe's fundamental nature and the practical implications for human technology and survival. As we continue to explore the universe, events like GRB 221009A not only provide grand displays but also valuable lessons about the universe's wild, untamed energies that, under the right conditions, could pose a threat to Earth. The collaboration and dedicated work of scientists like Gödel and Marguerite highlight the best of human curiosity and ingenuity. Their research into the violent deaths of massive stars and the resulting gamma-ray bursts helps us grasp the complex, often perilous nature of the universe, provoking both awe and a measured caution as we peer into the cosmos. In sum, the study of gamma-ray bursts merges the quest for theoretical knowledge with the practical need to safeguard our planet. As we decipher more about these powerful cosmic events, we not only satisfy our curiosity about the universe but also enhance our preparedness for potential future challenges. This work, while complex and sometimes daunting, is crucial for advancing our understanding of the universe and ensuring humanity's long-term survival in an unpredictable cosmos. As we delve deeper into cosmic mysteries like GRB 221009, we can't help but wonder, what if such a burst were closer? What unexpected consequences could arise? Comment with your thoughts and subscribe to explore more about the universe's profound phenomena with us.